This is our sixth and final video about concave mirrors and the images they form. In the last few videos, we've talked about what happens as you move the object closer and closer to the mirror. And in the last video, we specifically looked at what happens when that object is located at the focal point. And as you can see over here, when DO is 4, focal length is 4. So when DO is 4, the object is at the focal point. The image distance is essentially it's undefined. It's not zero, mind you, it's undefined. It's infinity, if you will. There is no image because parallel light rays never intersect, so no image is actually formed. In all these other examples, the reflected light rays bounce off the mirror and actually intersect somewhere over here. All right, and of course, as that gets farther away, the image gets closer. As it gets closer, the image gets farther away. But at this one special point, no image, parallel light rays. The light rays are parallel when they're reflected. So of course, there's no image height either. Now, what I asked you at the end of the last video was, all right, so having seen all of this, predict now what's going to happen when this object gets in front of the focal point, when it's between the focal point and the mirror. So did you take a moment to make that prediction? If you haven't, take a moment to predict that now. You can go ahead and pause while you think about it and make your prediction. All right, so are you ready? Let's see what happens. Did you see what happened all of a sudden? Did you see on the right side or behind the mirror those dashed lines all of a sudden appear? Now, those are not real dashed lines. I mean, they aren't real light rays. On the left side of the mirror, those represent actual light rays that actually either go to the mirror or reflect off the mirror. But what happens when the object, and I'll move it far enough forward so you can see what's happening here. When the object gets closer and closer to the mirror, the light rays reflect off the mirror away from each other. See these two light rays over here? These are the actual reflected light rays. Now, they never actually intersect. The word we use to describe them is that they diverge. They move farther and farther apart. So they never actually intersect. But they are also not parallel as they are here when there's no image, when the object is at the focal point. So while they never actually intersect, because they're diverging, there appears to be a point behind the mirror from which those light rays originate. The light rays appear both to be coming from a point behind the mirror. Are they actually coming from a point behind the mirror? No, because light rays can't go through a mirror. So the light rays aren't actually coming from here. They're coming from here. But because of the way they reflect off the mirror, and because those reflected light rays diverge, there appears to our mind that is looking at these light rays, our brain plays a trick on us. And our brain tells us, oh, there must be a point behind the mirror where those light rays do intersect. This image behind the mirror that you'll notice is right side up is what we call a virtual image. It is upright or right side up. It is behind the mirror because it's not an actual real image. Real images are formed where reflected light rays really intersect or actually intersect. These reflected light rays do not. But because they diverge, because they move farther and farther apart, they appear to intersect behind the mirror, which is why our eyes see a virtual upright image of the object behind the mirror. Now, a couple of things you should notice about that image. First of all, yes, it's right side up because it's virtual. Secondly, you should notice that the image is larger than the object. You can see here the image is larger than the object. If I move that closer, it's still going to be larger than the object. Not as much larger, but still larger. I move it a little farther away. Yeah, now it's so far away and so large we can't even see the top of it, but there it is way over there. Okay. So as the image moves closer to the mirror, it gets actually at this point smaller and smaller. It gets really big first, but then it gets smaller and smaller and smaller. Okay. But the whole time it's going to be right side up and a virtual image on the other side of the mirror. So that's the one time you get a virtual image in a concave mirror. Remember, in plane mirrors, you only get virtual images. When you get up in the morning and look at yourself in the mirror in the bathroom, you're always right side up. It's always a virtual image. But with a concave mirror, sometimes you get real images. One time you get no image. And sometimes when the object is really close to the mirror, you get a right side up virtual image. But I'll also point out that that right side up virtual image is always larger than the object. If any of you has ever shaved with a shaving mirror or done makeup with a cosmetics mirror, guess what? They're both basically the same. They are curved so that when you get up really close to them, you see a larger image of yourself. You can see your face better because it's bigger. Dentists use a curved mirror like this when they're looking at your teeth. Not only does that mirror help them see parts of your teeth that are hard to see without a mirror because they're way in the back of your mouth, but the mirror is curved so that it enlarges the tooth, or more specifically, it enlarges any problems, build up plaque, cavities, anything like that, so the dentist can see them more easily. But that's one or two of the common uses of a concave mirror. All right, so let me remind you that on Wednesday, we are going to have a quiz on the rest of the learning targets from this unit, except for number 13. I'm not going to I'm not going to ask you actually to draw these ray diagrams, but I will expect you to know what kinds of images are formed based on where the object is. So please review all of these videos. Please practice using your mirror equation and your magnification equation so that you can solve these problems. And we will have a quiz on Tuesday on learning targets 10 through 19 from our unit. Good luck, everybody.